Testing. 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 All right, I think the volume works. Sure, we don't have any bleed over volume here. Okay. Hope everybody had a good weekend and welcome to another Hoopo stream. Today we're going to be looking at a paper called Teaching Clip to Count to 10. This is a paper recommended by someone on our Discord channel. So go ahead and join that if you haven't. We like to talk machine learning and research and what the future holds with AI. So this work is coming out of 3 different groups here. We have Google Research, Tel Aviv University. Tel Aviv is a city in Israel. And then Weizmann Institute of Science. I do not know where that is from. Let's see. Weizmann Institute of Science. Weizmann Institute of Science is a public research university in Israel. Okay, so 2 different Israeli institutions here, and then Google Research. This paper is super fresh, just coming out less than a week ago. So let's see what this big eye-catching figure is. Here in the very front, the first figure that the researchers have decided to catch our attention with. Counting aware clip, we demonstrate the effectiveness of our improved clip. So clip is a contrastive language image pre-training model, which is basically a combination of vision and language in the same model, usually trained with a contrastive loss or some kind of unsupervised loss. So we have an image retrieval using text captions with different types of objects and their counts in the image. Images that match the caption are marked with check, and images that are not match are marked with X. Okay, so we don't really know what match the caption means. I'm assuming there's some kind of threshold there between the embedding of the words. So clip allows you to get an embedding for word tokens, such as 3 animals or 3 lamps, and then it also allows you to get an embedding for images, such as this image here. So I assume what they mean by match is that the embedding for 3 lamps is not sufficiently close enough to the embedding for this image here. And largely what they're showing you here is that the original clip model, so sounds like they're going to be doing some fine tuning or some additional training on clip itself. But what they're showing you is that the original clip model does not perform very well when it comes to counting. So there's 2 ways to really interpret this. One way to interpret it is that the word tokens for 9 and 6 and 5 don't have a very kind of strong association with the visual concept of multiple objects and specific numbers of objects. Different ways to interpret it is that it's actually very difficult with whatever vision encoder that clip uses to kind of have a notion of exactly how many objects are there. Usually a lot of vision architectures try to be spatially invariant and do things like average pooling, and as a result of those, knowing the difference between dogs and 3 dogs is not necessarily something that the learning objective and the loss encourages. Okay, so let's keep going here. Our model retrieves images that match the requested number of objects, while the baseline clip option retrieves images that depict the wrong number of objects. Okay, so the word retrieve here makes me think that what they're doing is they're finding the image that most closely matches, basically the image that is closest in embedding space to the word tokens for 9 hearts. Attention maps demonstrated that our model focuses its attention to matching objects instances in the image as opposed to the original clip. Okay, so here they have a kind of a relevancy map. Another word for these is called saliency maps as well, but basically You take an image and then you overlay on top of it an image that shows you which parts of the image are being paid attention to by the clip model. So here you can see that the clip model is mostly paying attention to the finger of this person, right? And here you can see that after the fine tuning, the model is mostly paying attention to the fact that there's 5 stars here. Interestingly, the word 5 I think is especially interesting because 5 is the number of fingers that we have on a human hand. So maybe part of the reason the original clip focuses on the hand here is that the word 5 is like kind of more strongly associated with fingers and high five and hands. So clip thinks that 5 refers to a hand concept rather than 5 objects. And obviously I haven't even read this paper yet, but I think this is going to be part of the issue, and I hope that they touch on this, is that when you take something like clip, and I'm sure they're going to fine tune it so that it performs better on this more narrow task of counting objects, it could make clip worse at other things, right? Such as identifying a high five, right? Maybe the association of high five and the word 5 with hands will go away, and you'll see clip become worse at other tasks. So something that you find often is that when you take a model that's been trained on either a very generic loss or some kind of unsupervised loss, and then you fine tune it for a specific task, it'll lose its ability to perform well across a variety of tasks. So you a lot of times have to trade off between a model that is more general and more capable of solving many tasks and a model that is more specific and performs very well on a very specific task. So we'll see if they touch on that, but I think it seems like their main objective here is to simply make a version of clip that is very good at counting. And a little sneak peek here for you guys. If you've ever seen my eyes flicker, I use this thing called NVIDIA Broadcast eye contact. So anytime my eyes get close enough to the camera, you'll actually see a fake eye get rendered. So you see it there. See that fake eye. So if you're ever looking at my eyes and they look a little weird and buggy, that's what's going on. I have basically fake eye contact. All right. Large vision language models, VLMs. I don't know. I haven't necessarily heard this 3-letter acronym. Most people just refer to it directly by the name, such as CLIP. Learn a rich joint image text representation, facilitating advances in numerous downstream tasks, including zero-shot classification and text-to-image generation. Nevertheless, existing VLMs exhibit a prominent, well-documented limitation. They fail to encapsulate compositional concepts such as counting. We introduce a simple yet effective method to improve the quantitative understanding of VLMs while maintaining their overall performance on common benchmarks. Specifically, we propose a new counting contrastive loss. Okay, so here we go. Here's the task-specific loss, and then they're going to be using this to fine-tune the pre-trained clip model, probably. Our counting loss is deployed over automatically created counterfactual examples. Okay, so they have some kind of synthetic data generation going on, each consisting of an image and a caption containing an incorrect object count. Okay, so I hope there's not a human labeler in this. I like the automatically created, but we'll see exactly how that happens. For example, an image depicting 3 dogs is paired with the caption 6 dogs playing in the yard. Our loss encourages discrimination between the correct caption and its counterfactual variant, which serves as a hard negative example. Okay, so hard negative example mining. So one way to think about what hard negative examples are is rather than teaching as a model with some kind of supervised law, such as this is a cat, this is a dog, this is a cat, this is a dog, your negative examples is basically this is not a cat, this is not a dog, this is not a cat, this is not a dog, and so on. And sometimes pushing the model parameters away from a specific answer can be just as useful as pulling them towards a specific answer, right? So supervised losses tend to pull the model into a specific place, right? Your gradient descent is pulling you towards a function being approximated that is good at that, and then you can also push away from bad places. And contrastive learning, such as the learning that's used in CLIP, uses both of those, right? It's not just this is a cat, this is a dog, it's this is a cat, this is a dog, this is not a cat, this is not a dog, and it alternates between kind of all of those, pushing and pulling in the high dimensional manifold that the language model and that the vision language model, or VLM here, finally learns. Okay, to the best of our knowledge, this work is the first to extend CLIP's capabilities to object counting. We introduce count bench. Okay, so a new benchmark. For evaluating the model's understanding of object counting, we demonstrate a significant improvement over state-of-the-art baseline models on this task, and we leverage our count-aware CLIP model for image retrieval and text-conditioned image generation, demonstrating that our model can produce specific counts of objects more reliably than existing ones. Since the advent of CLIP, training large vision language models has become a prominent paradigm for representation learning in computer vision. Yeah, the shared embedding space that is created by these large vision language models is very useful for a huge variety of tasks. But it's also useful because big pre-trained models are somewhat rare. So up until a certain point, all we had available in the computer vision community was ImageNet trained models, and then you had COCO trained models. And these large vision language models, such as CLIP, the fact that you can use them, they're, I think, pretty sure they're MIT licensed, that is a huge advantage. And it's not just specifically about the vision and the language being in the same model. It's also because they're just trained on a huge amount of data, and it's very difficult to get that kind of pre-training in-house unless you're a giant company. So CLIP, of course, is trained by a huge amount of data on a huge amount of compute. So it's also useful just because of the scale. All right. By observing huge corpora of paired images and captions crawled from the web, these models learn a powerful and rich joint image text embedding space, which has been employed in numerous visual tasks. They have classification, segmentation, image captioning, editing, blah, blah, blah. Despite their power, prominent VLMs such as CLIP and BASIC, so here's another VLM, BASIC, are known to possess a weak understanding of compositional concepts such as the relation between objects or their number present in image. It's demonstrated in Figure 1. CLIP often fails to retrieve images that correctly match the described number. Downstream applications that rely on VLM-based representations inherit these limitations. Yeah, so maybe specific here, I guess they give the example of image generation. So when you're doing text to image generation, such as stable diffusion or something like that, these models are not very good at rendering specific amounts of things. So if you tell it to render 3 dogs, the word 3 is kind of lost there. In this work, we focus on the counting task and introduce a novel method that enhances the quantitative understanding. We hypothesize that the reason existing VLMs fail to learn the concept is twofold. Captions that accurately specify the number of objects become extremely rare in the data as the number of objects increases. Okay, so basically there's kind of a lack of counted objects when it comes to the actual data set that something like CLIP is trained on. We found that for more than 6 objects, captions would typically contain a general form of quantity, a group of, or many, rather than an accurate count. Even with such examples in hand, the task of counting, i.e. associating the visible number of objects with an image in an image with the number in the caption, does not sufficiently contribute to the VLM's discriminative training objective. This is because other textual and visual features, such as noun and object categories, are often more informative for associating an image with its true caption. Yeah, so this is another interesting point here, right? Is that especially if you're using something like a vision transformer, right? A transformer being a type of neural network architecture that uses kind of the fundamental concept of attention. So these attention mechanisms, right? It's going to learn to pay attention to parts of a sentence that are going to help it the most with achieving its task. So if you have a sentence such as up here, we have something like 5 dogs, 3 dogs. The attention mechanism is going to learn to focus on the word dog because that's going to give you a lot more kind of bang for your buck when it comes to actually identifying pictures of dogs. So there's definitely, I definitely agree with kind of what they're saying here, where the data itself is not, the data and the loss itself are not really pushing VLMs to have this ability to count. So it's not their fault necessarily. It's the data set that they're trained on, and the training objective that they use is not quite right for counting. And that's where these guys are going to come in. That's where this paper, they're setting us up here to suggest the solution. So they're going to do this by creating suitable training data in which the captions contain accurate numbers of objects, and then designating a training objective whereby understanding object counts is critical for discriminating between the correctly associated captions and the incorrect ones. So they're going to create extra data, and then they're going to create a better loss. And then they're going to probably just fine-tune CLIP on that for some amount of time. We automatically create a clean and diverse counting training set by curating image text examples where the image depicts multiple objects and the caption expresses their count. To do so, we employ off-the-shelf computer vision tools to cross-validate the number of observed objects with the textual number in the caption. Okay, so it seems like what they're going to do is they're going to use some kind of generic object detection model, maybe like a YOLO, or if this is from Google Research, maybe like a MobileNet or something. Right? Like something small, something cheap that just basically counts bounding boxes, and then use that as a way to create captions for images. We then fine-tune a pre-trained VLM by formulating a counting as a discriminative task. For each example, we create a counterfactual caption by swapping the spelled number associated with the object count with a different randomly selected number. Okay, so here's kind of the negative example situation that we were talking about. So for each example, they're going to use a off-the-shelf computer vision model to actually count the number of things in that, and then they're going to have a true caption where you have basically the image and then the number of things in that image, but then they're going to create a couple negative examples where you have the image and then the wrong number of things in the caption. Boo, come yell over here. She wants to yell. Boo, come here. You want to come on the stream? No? He's afraid now. Okay, Boo. Do what you want to do. All right, to evaluate our method, we introduce CountBench, a carefully curated object counting benchmark consisting of 540 diverse, high-quality image text examples. We evaluate our method on 2 prominent contrastive VLMs, CLIP and BASIC, and demonstrate a significant improvement in accuracy in the task of zero-shot count classification over baseline models. Importantly, we achieve this while maintaining the original knowledge learned by the VLM, as demonstrated by an extensive evaluation of our model on standard zero-shot downstream tasks. So they are saying they are maintaining the original knowledge. We will see. Quantitative understanding of our model is further evident by our text-to-image retrieval results, as well as the relevancy maps, which demonstrate that the model correctly attends to all visible objects. Okay, and then finally they train a large-scale text-to-image generative model, which incorporates our counting training set. Okay, that's kind of interesting. They also train a large generative model with the fine-tuned clip model, and then show that the generative model actually is better. So, I mean, this is pretty good, right? I thought that this paper would kind of end here, and that they would basically just show you that fine-tuning on this specific counting data would improve performance on the specific counting task. But they went a couple steps further, and they decided to also show that you're not kind of doing catastrophic forgetting, as it's known sometimes, where basically the more you train on a task-specific problem, the less the model can generalize to other tasks. So they do this by kind of benchmarking their fine-tuned VLM on some kind of generic, probably detection and classification tasks. And then they take an extra step after that and train a generative model that uses this fine-tuned clip instead of the normal clip, and then show that this generative model is a little bit better at generating images that have specific numbers of objects. Okay, so ultimately they do 4 things here. They have 4 bullet points in their main contributions in their introduction here. So novel training framework for tackling the tasks of vision language counting. So this is their self kind of supervised, that includes a external vision model to generate captions. A new benchmark, this is their data set. Apply our method, demonstrating significant improvement, maintaining zero-shot accuracy on common benchmarks. So new training method, new benchmark or dataset, test dataset, showing that their fine-tuning doesn't mess with the original VLM accuracy on different tasks, and then finally training a new text-to-image generation model. Pretty good. All right, let's see what they have to say in the related work section here. Contrastive vision language models. Vision language models have demonstrated impressive success in vision and multimodal tasks, specifically multimodal tasks, right? Multiple modality here refers to the fact that you have the image modality and then the text modality. For example, sound would be a different modality. So anytime in machine learning you're using a variety of different modalities, I feel like you're always doing better. Generally, the reason people don't always do everything in multiple modalities is it makes training more difficult, because the training loss becomes more difficult, and then also finding a data set that has corresponding matching modalities is also very difficult. So finding for example, a text image data set is actually usually harder than just finding an image data set or just a text data set. But there are very good data sets out there that are multimodal, such as YouTube videos, for example, that has both audio as a modality, it has video as a modality, and then if you have subtitles, it has text as a modality. So I think multimodal is here to stay in the AI world. These models are trained on huge image text data sets and applied for downstream applications. We focus on contrastive VLMs, such as clip and basic. So contrastive here refers to the contrastive loss that is used to train these type of vision language models. Both downstream, blah, blah, blah. Okay, clip is trained on 400 million pairs of images and captions. So that's the data set that clip is trained on. where matching text and image pairs would have a low cosine distance, and non-matching text and images should be far apart. So this is the contrastive loss. Things that are similar should be closer in the embedding space, and then things that are farther away should be, or things that are not similar should be farther away in this embedding space. The model consists of a transformer text backbone and a VIT or ResNet vision backbone. Okay, so this is the important part here. So, well, it's one of many important parts, but the text is encoded before it is fed into clip. And that encoding is happening with a transformer, right? All kind of text is, I don't think anybody uses LSTMs and RNNs in text anymore. Like there used to be a little bit more heterogeneity in the architectures within natural language processing, but as far as I understand, it's pretty much all transformers now, and nobody does anything else. Within computer vision, there still is a little bit more heterogeneity. Sometimes people will use something like a ResNet, ConvNets, or a vision transformer. But I suspect that the more we advance and go into the future, the more you see specific kernels and hardware optimizations for transformers, the more you're going to see vision transformers as the go-to encoders or backbones for vision pipelines. So we'll see if they try both the VIT and the ResNet. Maybe they provide an ablation as part of this. I'd be curious to see if there is a difference between those. The representations computed by CLIP have proven to be very effective in vision and multimodal tasks due to their zero-shot capabilities and semantic nature, and have been widely used as a prominent component in numerous tasks and methods. BASIC scaled up the size of the model and uses CoatNet for its vision backbone. Okay, so BASIC is a larger version of CLIP, it seems. And it uses CoatNet. Wonder what CoatNet is. Is CoatNet a ConvNet-based model or a transformer-based model? Compositionality and counting in vision language models. While demonstrating impressive recognition capabilities, large VLMs such as CLIP and BASIC are known to only partially capture the meaning of the text. Numerous works have shown that they fail to understand compositional concepts such as relationships between objects or their number in the image. Okay, CLIP tends to attends, so basically what is it paying attention to? It's basically mostly paying attention to nouns. Often ignores adjectives, numbers, and prepositions. Okay, so here we have the method overview. So I guess we can wait until we get to the method section to read it. Let's finish the related work here. Counting has remained a standalone task under the domain of visual question answering. So counting is a specific task that people have tried to do before, and here they're saying that it's within the general sphere of VQA, or visual question answering. And here are some specific approaches that people have used to counting. A layer that infers the number of objects from the normalized attention weights. Relation networks to model the relation between foreground and background. Some very specific kind of architectures there for counting. While previous efforts are restricted to VQA and problem formulation, our goal is to improve the quantitative understanding of general purpose contrastive VLMs. Yeah. So this is smart. I do like this, where basically it would have been very easy for them to just simply fine-tune this and create a model that is very specialized for counting, but the authors here are clear and they understand that having a very task-specific network is actually not very useful, and you want to be able to take a general model, fine-tune it so that it's better on a specific weakness, and then still have a general model. And here, right, you still want to be able to use this fine-tuned CLIP and this fine-tuned BASIC for other tasks that aren't counting related. unlike prior methods, which can be problematic for new domains. Okay. Text condition generation. So here's a little related work section on, I wonder if they mentioned Stable Diffusion. No, they're going to mention their own stuff. The field of text image generation has made significant progress, mainly using CLIP as a representation extractor. And a lot of people use CLIP, but then again, that has also a lot to do with the fact that it's available for use. CLIP to optimize a latent vector in the space of a pre-trained GAN. Others utilize CLIP to provide classifier guidance for a pre-trained diffusion model. This is probably Stable Diffusion here. And employ CLIP to optimize a deep image prior model that correctly edits an image. The field has shifted from employing CLIP as a loss and into using it as a backbone. Okay. In huge generative models. What do they mean by that? Resulting in impressive photorealistic results. However, these methods inherit the limitations of the VLMs. Text-to-image generation methods that use CLIP fail to reliably produce significant counts for objects, or specific counts for objects. While several attempts have been made to improve the correspondence of text-guided generated images, their focus on the generative pipeline, while we attempt to improve the text representations themselves. Okay. So nice little related work on kind of the generic stuff here. Let's scroll up here and look at the actual method overview here. So the architecture diagram is another name, or system pipeline, or whatever you want to call this. Who decided to use trapezoids, right? Who was the first person to use a trapezoid? We create text image counting set in which each caption expresses the number of objects detected in the corresponding image. This is done using an off-the-shelf object detector to automatically identify text image examples in which the text count matches the number of visible objects in the image. Okay, so this is the part where they actually generate a data set using a off-the-shelf object detector. So here, this object detector is something like YOLO, right? YOLO is a bounding box model. It outputs a bounding box, which is this little red box here that you see on each of these three horses. So it'll look at a picture of a horse and it's just going to tell you here are three different objects in this image, and each of those is a horse. So the object detector does not have any notion of the text. So the object detector is not receiving the text, it's just receiving the image, and it's giving you these bounding boxes. And then they have some kind of hard-coded stuff here that says, okay, if there's three bounding boxes and the caption has the word 3 in it, then we're going to say it's a match. And then we're going to say this is going to be one of the examples that we're going to use in our fine-tuning data set for CLIP. So I guess they basically just run a giant data set that they have through this object detector, and all the times when the object detector and the caption happen to match on the number of things, they will put that in a separate little folder, and then that separate little folder will become the data set which they use to fine-tune the CLIP model. We fine-tune a pre-trained CLIP model using our counting subset through a dedicated contrastive learning objective LCount. Okay, so they're calling it the counting subset. That's the separate little folder that we just mentioned. And then they have a dedicated contrastive objective LCount. So this is a new supervised, loss function here, not supervised, but a new loss function LCount, used in addition to the original generated text image contrastive objective LClip. So it seems like maybe what they might be doing is they might be using both losses. So this might be how they maintain the general capability of the CLIP model, right? If they would have only pushed gradients with this counting loss, over time the CLIP model would have become more and more narrow and less general. But by training with a combination of those, or some kind of like alternating training scheme where they train with the count loss and then they train with the clip loss and then back with the count loss, or some combination of those two, they can make sure that the clip model still maintains its original kind of general ability, but then it also has the improvement in the narrow domain of counting. Okay, so specifically given a text-to-image example from our counting dataset or subset, we automatically create a counterfactual prompt by replacing the true object count in the original caption with an incorrect count. So here's where they're going to do the contrastive part of their new counting objective, right? So contrastive here, they're going to have the true object count, and they're going to try to pull the embedding. They're going to push gradients such that they pull the embedding closer to the true object count. And then they're going to have the wrong object count here. They're calling it the incorrect. So here they might have this picture of the 3 horses, and they might say 4 horses running. Here you go. Perfect. Here you go. So they have the counting subset. Here's the images of the horse with 3 horses running. And then they're going to basically change the numbers and say these are negative examples. So you see here they're feeding this example here into the clip text encoder, so 3 horses running, 4 horses running, and then they're also feeding the image itself. So they have the image, the caption, and the counterfactual caption, and they want the image and the caption to be closer together in embedding space, and then they want the image and the counterfactual caption to be further away from each other in the embedding space. And interestingly here, note how the caption and the counterfactual caption, there's no loss between these. There's no contrastive loss here, right? So they're not pushing the caption away from the counterfactual caption. That wouldn't serve them. So they're pulling together the caption and the image, and then pulling apart and then pushing apart the counterfactual caption and the image. Here you have the 2 parts of clip, right? Clip is both text consumer and an image consumer. So here you see how the images are coming in through the image encoder, which is going to be the VIT, the vision transformer, or a ResNet, or some kind of CompNet or something like that. The text encoder is just going to be a transformer. And then here you see an attention matrix. I guess the green is what is this? Okay, so the black is this. I don't know what they mean here, but I think the black is the text, and then the green is the image. No. The green is the caption. Damn, like there's too many colors here. The border color of this box is black, but the word 3 is also black. So what does this black refer to? Either way, the clip loss is very similar to this kind of idea, right? Where the clip loss, what it's trying to do is it's trying to pull together the image and the caption, right? It's a contrastive loss as well. So I think this part here is the most important part, right? Where basically what you're doing is your loss is pulling together the word 3 in 3 running horses, and then the image of the 3 horses, and pushing apart the word 3 and the 3 horses from 4 running horses. Well, not the word, not word with word, just image with word both times. Right. Hopefully I made that sufficiently as confusing as possible. And let's go to the actual text description of this. So method. Our method is to teach a pre-trained VLM, e.g. clip, to count, i.e. to improve its quantitative, textual, and visual understanding. We first automatically create a counting training data set, okay, comprising of clean and diverse images along with corresponding captions. We then leverage this data set to fine-tune a VLM through a designated count-based contrastive loss that is used in tandem with the original generic objective. Fine-tuned through a designated count-based contrastive loss. More specifically, our key idea is to automatically generate counterfactual examples by swapping the true object count with a different random number. Our new counting loss encourages the model to embed an image close to its true count as expressed by the original caption, while pushing it away from the embedding of the counterfactual count prompt. As the only difference between the correct caption and the counterfactual counterparts is a single word, the spelled number of objects, the model has to distinguish between the correct and incorrect count. Creating an image-to-text counting train set. The naive approach for obtaining an image-text counting dataset is to filter a large-scale dataset by considering only the examples in which the caption contains a number. Okay, so this is how they get the original dataset. Right, because we don't know how they get this one here. So we know how they take a data set that has captions and images and then use an external object detector to basically find a subset, which they called the counting subset. But we don't know where they get this original data set from. So sounds like here what they're saying, they still don't even tell you. They say filter a large-scale data set. So what is that data set? Where did they get that? Recall the crux of our method is a contrastive loss with respect to hard negatives which differ from the original caption. We exploit several stages of automatic filtering. We filter out all examples whose caption does not contain a spelled number. Okay. We do so as we observe that non-spelled numbers or numbers higher than 10 appear mostly in conjunction with measure of time or addresses. Yeah, this is another reason too, right? So like maybe the reason that clip is bad at counting is that a lot of times the number is kind of like a red herring, like you, as clip is sitting there training on the original clip loss and it gets pictures of like a house with an address number, maybe it's trained on like a large data set of like real estate images such as Zillow or something like that, right? The clip model probably will learn to ignore the numbers because the numbers generally don't really help it identify whether it's a house or whether it's a dog or something like that. It focuses on the nouns. So the way that the clip model is originally trained is, in a sense, pushing the clip model into a particular area of kind of function space, right? And ultimately the model is just approximating some kind of function, but it's pushing it into an area where ignoring the counting and the numbers is actually better. So it does make sense that clip is going to be bad at counting in the way that it's been originally trained and on the type of data set that it was originally trained on. Only then can we use this and then replace the number to create negative caption. So here they specify positive caption versus negative caption. So positive caption is going to be 3 horses, negative caption is going to be 4 horses. We assume that the caption refers to the most prevalent object in the image. Wonder how much this assumption is, how important that assumption is. Thus, we retain only examples for which the number specified in the caption aligns with the number of instances of the maximally detected object. We denote by C our automatically filtered train set. Okay, so this is going to be a mathematical term here. Let's see what this example here is, or this figure. Examples of image captions where their numbers are not related to the object counts. These are automatically filtered out by our method. Okay, so actually here you go. This is a good example of kind of what we were hypothesizing on, that clip actually has many examples of images where you have to ignore the number. So here you have a picture of like a little pagoda type thing and then 10-minute walk to village. So here the word 10, clip in its original formulation, is learning to ignore that. My Westy iPhone 5 case, right, it's also learning to ignore this 5. So you see how time and again, there's plenty of examples here where clip is like just learning to ignore the numbers. Naturally, the filtered data C is unbalanced. The number of examples that pass our filtering drops significantly as the count increases. The number of 10 image pairs is around 1000x smaller than the number of 2 image pairs. Training with such imbalanced data set creates a bias. That's a word that's popular nowadays, where basically people are becoming more aware that your model is going to reflect any bias that's in the data set. So In this case, it's not super important because you're just counting things in an image. But like if you were training a model to approve loans, right? You would have to be careful about bias there. So bias is the word of the moment. Therefore, balancing the data is of essence. Due to scarcity of examples depicting more than 6 objects, we choose to balance the numbers 2, 6 separately from the higher numbers 7, 10. Okay, we sample 37K samples. There are approximately 7K samples down to 1.5K. Okay, so what is the final size of C? They don't tell us. I'm guessing it's like 50K. All right, section 3.2 here, teaching clip to count. Our goal is to improve the quantitative understanding of a pre-trained VLM while preserving its real-world knowledge. Therefore, we use a combination of 2 loss functions. All right, so here's the final loss function that they're going to be using for this fine-tuning process is the combination of the original contrastive clip loss and then their L count, which is the counting designated loss. And this little lambda here is going to be a hyperparameter. So they're going to choose a number for this lambda that sufficiently balances these two. And this is like one of the problems with these type of multi-part losses is like whenever you use a loss that is composed of many other smaller losses, you're going to basically have to have these hyperparameters that weigh or discount specific losses over another. And those hyperparameters are, you have to basically choose them by hand. So most people don't pick them by hand. They kind of pick a guess and then they'll use hyperparameter sweeping in order to figure out a value that is good for that. But you can imagine how if you had 10 terms here, 10 different losses, the parameter space of these different weighting parameters would be huge, and it'd be very difficult to find the magical combination of these hyperparameters in order to properly weigh the losses. So there is a limit to just putting all the losses together. Fine-tune the model on 2 training data sets, a very large data set collected from the web. So, I mean, they still haven't told us what this is. I think maybe they're gonna call it count bench. Our filtered number training set, C, and where L clip is calculated on all samples, the counting loss is calculated only on samples from C. How do they do that? What happens when the C is in the image is in clip but not in count? For each image text pair, okay, so we have a pair of images in text. So IK and then TK. Text is the T is the text, I is probably the image, and then here they're telling you that both this pair of image and text is inside C. So that's what that little like trident E sound, E symbol means. It basically means in the set of C. Counterfactual caption. So TK is going to be the true caption. So in our earlier example, this will be the image of the 3 horses would be IK. TK would be the text 3 horses. And then TK CF here, which is the counterfactual caption, would be 4 horses. Okay, after each training set, the triplet, okay, so now your tuple, right, of image and text is now a triplet. It's now an image, a text, the wrong text, the counterfactual text. And there's K of these, right? K is basically the size of the counter or the data set C, the subset C, are then fed into to obtain their embeddings. Okay, so clip has text and image encoders. So here, these kind of like orange, yellow bricks here, these are encoders. They take something raw like an image or something raw like a text in sentence, and they turn it into an embedding, which is basically just a vector in some high dimensional space. And you see here how the original image and text, they're calling it IKTK, but once you turn it into an embedding, they're going to call it EIK, ETK, and then ETKCF. So EIK is not like the multiplication of E times I, it's an embedding produced by the image IK. A contrastive loss L count is computed to enforce that the similarity score of the image is high with the original caption. Okay, similarity score of the image is high with the original caption and low with the counterfactual caption. Okay, so here, this is the actual loss. So this is the actual function that is pulling the embeddings for the image and the similar caption together, and that is pushing away the embeddings for the counterfactual caption and the image. So you see here how they have image times caption, image times caption, and then image times counterfactual caption. And they're basically taking the exponent of all of those terms, and then this is image caption over image caption plus image caption times counterfactual caption. So 1 over n, k equals 1 to n. So k is the index of, I think n is the batch. So this is not, you're not going to be able to feed the entire subset capital C at the same time. So I think K might just refer to a batch of images. So K is like the index within the batch. So for all images in which you're evaluating this specific loss right now, there's going to be n of them. You're going to sum this over all of them, right? Divide by 1 over n. Negative just so you can decrease it, right? You want the loss to go down over time. And then that'll give you the count loss, which is then multiplied by this weighting hyperparameter here, lambda, and then combined with the original clip loss. So there's a couple things that we still don't know yet. They still haven't told us what K is. They still haven't told us what capital N is. And they still haven't told us exactly how they're creating these batches. So because the way that they describe it here, L-clip is calculated on all samples, but the counting loss is only calculated on samples from C. Are they training on only samples from C? Are they training on some combination of samples from C and all samples? What happens when you're training on a sample that is not in C? Do you zero out the L count? So a couple of things they still haven't answered there, but so far we're getting a pretty good idea of kind of what they're doing here. This loss encourages the model to learn the relationship between the specified number and the number of objects it refers to. We use the negative samples only in the counting objective L count instead of adding them to the batch for the existing contrastive loss L clip. Okay, so there's some kind of alternating going on here, like there has to be. Because the negative examples are only used for L count. We test our method with 2 classes of state-of-the-art VLMs, basic and clip. For clip, they have 2 different sizes of clip here. And then for basic, they use, I guess basic S is probably the small version of basic. We fine-tune all models for 20K steps using a cosine learning schedule, so initial learning rate of 5e to the negative 6. So a learning rate schedule, and sorry if I keep explaining these terms over and over again, but I figured being kind of an educational channel, it makes sense for me to explain things such as learning rate scheduling. But your learning rate is going to be how much you move in model parameter space with each iteration, right? Ultimately, you're doing a gradient descent step, right? So you can think of the magnitude of that step roughly being determined by the learning rate. And what you're doing when you're doing a learning rate schedule is you're changing what the step size is, right? So initially when you train, you're going to take bigger steps than when you get closer to the end of training, right? As you get closer and closer to your ideally global maximum, but realistically local maximum and local minimum in model parameter space, you're going to want to take smaller and smaller steps because you're going to be closer and closer to the hill, right? And you want to basically like kind of narrow down right on top of the hill. So that's why people will use these learning rate schedules to slowly decrease the learning rate over time. And note how this is already a pretty small learning rate, 5e to the negative 6, which is important because if you're fine-tuning a model, right, that model probably the last 25% of that model's training was done with a very small learning rate. So if you suddenly start trying to fine-tune a model with a huge learning rate, what's going to happen is you're just going to very quickly overwrite the progress of the last model training session. So when you're fine-tuning a big pre-trained model, starting with a smaller learning rate is generally a good idea. So they have an absolutely monster batch size of 32,000. This makes me think that their batches are directly in embedding space. Yeah, so you can't have a batch size of 32,000 images. That's just completely unrealistic. There's no GPU in the world that can fit that in memory. So I think what they're doing is they're taking their entire data set, they're converting it into embeddings. Embeddings are just going to be vectors, so they're going to be much lower dimensional, much easier to deal with computationally and shuffle them around and stuff like that. So I think that's what they're doing here. Where a fraction p over 132 of each batch is dedicated to samples from the counting training, and the rest are large image text data sets collected from the web. We use a gamma of 1. So here's the magic number that they settled on. And use a linear warm-up for the first 10,000 steps. We introduced a new object counting benchmark called CountBench. Okay, so this is their new data set. Automatically curated and manually verified from the publicly available Leon 400 mil. So maybe this is the one that they used. CountBench contains a total of 540 images containing between 2 and 10 instances, so it's a very small test data set, but I guess that makes it easy for people to benchmark their models against. Between 2 and 10 instances of a particular object, the images in CountBench were obtained by first running our automatic filtering model described in section 3.1 over the entire Leon 400 mil dataset. This filtering produced over 158K images for the number 2, but only around 100 for 10, demonstrating again the severe number imbalance we encountered with our training sets. After automatically balancing each number to 100 and 200 samples, the entire dataset is manually verified. Blah, blah, blah. Okay. It's worth noting that the higher the count is, the higher the proportion of CountBench images which contain relatively simplistic 2D collections of objects as opposed to objects in real-world scenes. Yeah, there's all kinds of like weird associations and biases when you're doing this. Right, so here they're saying that something like 9 or 10, once you get to these higher numbers, the images are going to be more contrived, right? Like this isn't a natural images of 10 chairs. It's like 10 chairs on a weird white background. So the lower your numbers, such as 2 or 3, the more natural that image is going to be. So here you have, of course, like a very natural image of 3 dogs on a beach. These are pretty cool little benchmarks, or cool images. I like these. This one has a Shutterstock, or not a Shutterstock, but like some kind of watermark. Confusion matrices on CountBench. Classification accuracy on our new counting benchmark CountBench, broken down into confusion matrices for the public clip VITL14 and our improved clip VITL14. So this is a specific size of clip, and the VIT there refers to the fact that the image encoder is a vision transformer. So here you can see the confusion matrix. So a confusion matrix is generally you see these in the context of a classification task. So in a classification task, you might have a bunch of different categories such as cat, dog, chair, plane, car, whatever. And then you basically have the same categories on the x-axis and the y-axis, and then the square here is letting you know how many times the word 7 was miscorrectly classified as the word 2, right? So this isn't a classification problem in this sense, but it's very similar in that largely you're classifying these images into either having 2 something, 3 something, 4 something, and so on. So you can see that 2 is very rarely misclassified as something else. And if it is, it's almost always misclassified as 3, right? So these are the higher numbers here. So you can see here how after they're fine-tuning on the specific counting loss that we've seen, you can see how clip is much better. The confusion matrix, this looks much better, right? You can see how this big chunk of zeros here, that's good to see. And then this big strong diagonal is also good to see. And you can see where it kind of gets confused, right? Where 6, 7, 8 are a little bit confusing, and then 9 and 10 are a little bit confusing for the model. And just comparing the difference between, for example, the baseline clip. So this is clip without any modification. You can just see how much better it is at this counting task. So this image here is, this to me is like kind of the smoking gun for this entire paper. This is like the cleanest image. Pretty much shows you that they did exactly what they said they were going to do in this paper. Okay. Experiments. We thoroughly evaluate our method both quantitatively and qualitatively. An object counting related task using our CountBench benchmark. We further validate that the performance of our fine-tuned counting-aware models on a variety of general zero-shot classification benchmarks is retained. To gain a better understanding of our models, we show visualizations of text-to-image relevancy maps along with per-word relevancy scores, demonstrating that our model indeed attends to the number of objects in the image and text. Finally, we apply our model to text-to-image retrieval and generation. Okay, so here's where they're going to actually do the experiments, and then they told us they're going to train a text-to-image generation model, so that should be interesting to see. All right, we're starting to get to the end here. We evaluate our models on CountBench. For each image, we augment the existing caption with 8 other possible captions by replacing the number. So this is the okay, so this is how they're actually doing the evaluation. So they feed the image into their modified clip, and then they're doing a similarity of that image to 10 different versions of the caption, which have 10 different versions of the number. So they're almost like ending up in the same place as like a classification head, right? If you have a classification problem and there's 10 classes, the final dimensionality of the final layer in your model is going to be 10 because there's 10 possible classes, and then those produce basically logits, which are then interpreted via softmax as probabilities, and then that'll be the probability for each of the 10 classes. But here they don't actually have a classification head, so what they're doing is they're basically just feeding the image into the clip image encoder. They're getting a little embedding vector, and then they're feeding the caption into the clip text encoder, and they're getting a little vector. And then they're comparing those two vectors, right? How close are those two vectors? How close are those two embeddings? And that will be the distance between the image and the text. And then they're going to find the distance between the image and then 10 other versions of that text where all they do is they just change the word that represents the number. And the number in the caption is the number that obtains the highest similarity score. Table 1 reports the result of this evaluation on two prominent contrasted VLMs. We compare our model with two baseline configurations. Comparing the performance allows us to quantify the effect of using our own large-scale text-image dataset. As can be seen, our method achieves significantly superior counting accuracy compared to baseline. So their method is going to be E in these tables, and the baselines are going to be A and B. Okay, so E is the full Monty, and then here these are smaller, or this is just baseline. So the difference here between official and internal is sometimes the official baseline is what you'll find on the paper. So the CLIP paper has some number for this. But internal baseline means that the authors took the CLIP model and then ran it themselves and got a different number. Like, there is a little bit of a reproducibility crisis within machine learning, and it's not necessarily out of malice. It's more so out of just kind of incompetence, I would say. It's just kind of, it's difficult to take someone's existing code. Sometimes they don't release the code, they don't release the data set, they don't release the testing data set, they don't really exactly tell you how they subsampled the testing data set. Like, there's so many different things that you could have different from the original implementation, from the original paper, that your internal baseline using a model such as CLIP is going to differ a little bit from the official baseline that is provided by CLIP in their paper. So that's the difference here as well between public and internal. So you can actually see here that the internal baselines are actually better than the public baselines, which is interesting. So I guess higher is better here. So that's what this little arrow here means. It means that higher is better, and then mean deviation from the correct number, this number lower is better. So you can see just how much better it is. It's like significantly better. And there's a little bit of an ablation study here where they show you the difference between the model that has everything that we described and then a model that does not have the advanced filtering and does not have the count loss. So C here is models trained with our filtering counting set, but without the counting loss. And then D is models fine-tuned on the counting loss on a naively filtered counting set. So we scroll back up. No counting loss means they get rid of this part here. So all they're doing is they're just basically fine-tuning it on some kind of counting subset. So it's getting a little bit more examples of counting stuff, but it's not using the specific contrastive counting loss that they specified. And then no filtering means they're not doing this part here where they basically filter the data sets using the external object detector, which we still don't even know what it is. They still haven't told us what that is. I'm guessing it's YOLO, but I don't actually know. Okay, so that's kind of the ablation study there, and we see that with both of those combined, you get a significantly better result than with either half of the method that they describe. Zero-shot accuracy on common benchmarks. Okay, so this is the proof in the pudding for whether or not everything that they've done and the fine-tuning and taking CLIP and making it better at counting, how much worse is that making you at other tasks? So the way that they're going to evaluate that is they are going to test their model, which has been fine-tuned on counting, and see how well it performs on things such as ImageNet and Food 101. And right, these are all just kind of like generic classification problems or detection. Like these are all just kind of generic data sets that are used as benchmarks. So you can see how here they actually do quite well here. You have 64, 64. You have 80, you have 80. Damn, it even does better sometimes. Look at this. 65, 67. Basic S seems a little bit more sensitive, so 61 and then a slightly lower version of 61. Here you have 66 and then 65. So it does seem like the basic model, this one here, is actually losing out by training on a task-specific data set such as their counting subset. So you are losing a little bit of performance here, right? And that's also the case here, right? You see going from 73 or from 80.72 to 80.53, you're just losing a couple points of accuracy here on these different benchmarks that aren't counting related. But this one here is the most interesting to me, is that you actually got an improvement on Oxford flowers, which to me means that there's something about the Oxford flowers benchmark or data set where having a better counting prior, or like some kind of like better awareness of the counting of objects, actually results in a performance improvement. So this might be the most interesting number in this paper, right? 65, 67 right here. The fact that you got an increase with this fine tuning. Okay. Table 1 also contains an ablation of the two components of our method, filtering and counting training data set, and fine-tuning with an additional loss, L count. Models with our configuration are fine-tuned on an alternative counting subset, which consists of all the samples that spelled numbers. As both configurations are fine-tuned over the samples, as can be seen, while naively filtered data does not improve performance over baseline trained with a dedicated counting subset, the obtained results are still significantly lower than those produced by our model. We attribute this gap in performance to mislabeled training samples in the naively filtered data, which is absent from our counting dataset C. Confusion matrices, these are we looked at, those were good. Our improved clip model is significantly superior to the baseline across all numbers. Yeah, I think this confusion matrix just looks so good, right? Like look at that difference between this one here with the baseline clip and then this one here with the fine-tuned on counting. And these actually look pretty good too. So performance on common non-counting classification, this also look pretty good too. You're not really losing that much performance, and in some weird situations such as Oxford flowers, you're actually gaining performance. Leads to only a slight shift in accuracy of the models on common benchmarks. Hyperparameters of our method. Our method introduces two additional hyperparameters, the portion P of the batch size dedicated to the counting subset. Okay, so they finally told us what that is. So if you recall in the method section here, it was a little bit uncertain exactly how they were creating batches of data for training here, right? Because they were saying that the clip loss is only used for non-C examples. The count loss is only used for examples in C. And so there's kind of this idea of like, okay, well, what are they actually putting in it batch to batch? Are they doing alternating batches of these losses? Like what is going on here? So now they finally explain it down here, and they say that there's this extra hyperparameter called P, which is going to determine how much of the batch is actually composed of images coming from the filtered subset C, and then just the unfiltered normal training data set. Table 3 contains an ablation for the choice of P and then compares the result. Okay, so they have the what I assume is basically the results from a hyperparameter sweep where they tried different values of p and different values of lambda and showed you how there's some values of those that are going to be more optimal than others. We considered the task of text to image retrieval, where the text explicitly describes the desired count of objects. Okay, for each category, we use the caption a photo of n objects. For each caption, we retrieve the 5 images in the dataset that are predicted by the model to be the most similar. Note that since there are no ground truth labels for the counts of objects, we present quantitative results. Where did you learn that much high-level math? Life. My original degree is in physics. It's not as scary as you think. Okay. Where were we? As can be seen with the requested number of images, when the requested number is larger than 3, the images retrieved often depict arbitrary numbers of objects. Baseline often retrieves the same images. This further implies that the baseline model mostly focuses on the existence of the described object and ignores number in the caption. Yeah, so this is kind of what they were describing before, where the original clip model actually has learned to ignore the counting and numbers. So that's what we expect to see here, right? Where with the original clip, you give it this image here, you put this image through the text, or you put this image through the image encoder, and then you put this text through the text encoder, and you can actually calculate not only the saliency map or relevancy map, as they call it here, for the image, right? And this is showing you which part of the image is the model paying attention to. But you can actually also get it for the text. So you can get a score that tells you how much is the original clip, how much is the original clip saying that duck is related to this image and the word to is related to this image. So one thing to notice here is that after the fine tuning on the specific counting subset that they've created in this paper, you can see how these numbers are much higher, right? So the clip model is paying much more attention to the actual number words as opposed to just the nouns, right? So nouns like pumpkins, ducks, and cards. So not only are you getting a much better kind of relevancy map and saliency for the images, but you're also getting it for the words as well. Model focuses on areas in the image that are relevant for counting. To gain a better understanding of what our model learns, we use an explainability method to visualize the reasoning of the model. For each image caption pair, we refer to the cosine similarity of their clip embeddings as their similarity score. This score should be high for a pair that clip considers matching and low for non-matching images. We use a method of Schiffer et al. To obtain relevancy maps, which consists of relevancy scores for each patch in the image and every token in the text. Okay, so the word patch here in the image is referring to the fact that they're using a vision transformer to encode the image. The relevancy score indicates the importance of different parts of the text and image in predicting the similarity score. Note that the relevancy scores of text are normalized to sum to 1. Examining the relevancy maps of the text, it is apparent that the relevancy score of the spelled number is significantly higher, which suggests that our model concentrates more on the mentioned number than the original one. And you kind of see the same thing as in the image. Model focuses only on relevant objects when the correct number is used, unlike the baseline clip model that highlights all objects. All right. And now I think they have beyond proved that what they did was useful and that it helped and that it didn't necessarily destroy clip. And now they're going above and beyond, and they're going to basically train a generative model with their special clip that they just trained, and we'll see how it does. In order to demonstrate the effectiveness, we are going to train an ImageGen model. So a little bit sad. The reason this is sad is that ImageGen is the Google model. So it's basically Google's Stable Diffusion. You can think of it that way. But the problem is that it's been trained on kind of proprietary data, so we don't have access to that. So because we're not inside Google, we don't have access to ImageGen, which is a little bit sad. So they're not gonna give us access to this model. Okay. Conditioned on textual embeddings, and another ImageGen conditioned on our counting aware. Yeah, so they basically have two different ones. They have one conditioned on the just vanilla clip, and then one conditioned on the clip that they have here, which is fine-tuned. I feel like they should have called it something else just to make it easier to tell, right? They should have called it like C clip for like counting clip. Most of it does not stick. Yeah, so I think with learning, it's not important that you understand everything. As long as you understand some things, you're fine, right? And then over time, you just learn more and more and more and more, right? And it's kind of like learning a language, right? Where initially when you're learning a language, you're not going to be able to pick out most of what someone's saying. You're only going to be able to pick out maybe one word or two. But then once you can pick out one word or two, then maybe you start to pick out 2 or 3 words, right? And then 4 or 5 words. And then over time, you'll eventually get to the point where you're understanding 99% of what anyone tells you in that new language. And then it's only rare when you run into something like a word that you don't know what it is. So yeah, don't worry too much about it. It's just time-based. It's just total time is the only thing that matters. You don't need to worry about being super optimal in terms of like what you're doing in each hour. Okay. We obtain additional set of prompts where number in 2, blah, 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 since the amount, additionally report the accuracy. Our fine-tuning approach leads to a 1.5 to 2x improvement in the ability to reliably generate specific counts of objects, as shown in table 5. So table 5. All right, so here is the generative models. So they have 2 generative models. They have one that uses the counting clip, and then which is the clip that is fine-tuned in this paper, and then one which uses the original clip. And here they're trying to generate an image, right? As you do in a text to image generative model, what you're doing is you're giving it a text such as a photo of 5 shirts, and then the model will generate images from that. So here you can see how when they say a photo of 2 shirts, the counting aware clip model, it produces 2 shirts pretty much every time. The original clip model also generally produces 2 shirts every time. So original clip is actually pretty good with just 2 and 3. But as soon as you start getting to 4 or 5 or 6 or 7 or like any of the larger numbers, you can see how the green means that it correctly generated 9 t-shirts, and the red means it incorrectly generated 9 t-shirts. So you can see how very quickly, as soon as you go over 4, the original clip is not able to do it. So this is not clip itself. This is a generative model called ImageGen, which is image generation, short for image generation, ImageGen. And you can see how it is not capable of doing that. And actually, the more interesting thing here is that it produces the same model. So a photo of 8 shirts and a photo of 9 shirts and a photo of 10 shirts actually produces the same exact image. Versus you see here with the counting aware clip, you don't see that kind of duplicated image. And in fact, it's pretty much perfect almost every time, except for some confusion in the 10 and 7 and 5. Same thing with trees here. As can be seen, the retrieval results of our model are significantly more accurate than the original clip model. Relevancy map between the image and different numbers. We compare the clip relevancy map. So here they have relevancy map for different numbers in the prompt. So you can see how the original clip model, right, it kind of largely ignores the numbers. So you can see how the relevancy map stays pretty much consistent for all of them. But the counting aware clip model from this paper, you can see how 1, 2, 3, 4, 5, you get a different relevancy map. Our method is limited by the insufficient existence of training data with images containing multiple instances of an object. Furthermore, many of the correct training pairs with higher numbers that do not exist contain relatively simplistic 2D collections of objects as opposed to objects in a real-world scene, and can explain the weaker model performance on in-the-wild images containing a large number of objects. Our method teaches clip to count to only until 10. See, the interesting thing with this is that I would say this is the case for humans as well, right? Like, as a human, you can look at a picture, and as long as there's roughly less than 10 things, you can probably count them in your head. But if I saw a picture of like 74 people in a room, it would take me a while to count all 74 people, right? So like even humans, we're going to have a very hard time counting above 10 in like a very busy scene, right? Like if I gave you a picture of like a NYC subway picture, right? Like even something like this, I don't know what the number is. I'd have to sit here and count in order to actually give you the number of people in that, right? Like here, I can tell you, okay, there's three people, 1, 2, 3, and then I guess maybe 4. So even as a human, like you're also limited to like roughly around 10-ish. So conclusions and future work. This work presents a first method to enhance clip with counting abilities, which is an essential step towards enabling more accurate retrieval and generation of detailed texts. Using a carefully designed filtering pipeline, we are able to obtain a clean counting subset collected from the internet, which we perform counting focused hard negative augmentation. An additional loss is applied that encourages clip to understand the object counting. They introduce a new counting benchmark, CountBench, which we plan to release publicly. Applying this method is not specific to counting and can also be applied to other compositional concepts. We focus on counting as it is the most unambiguous to define and evaluate. The extension of this method to other compositional concepts such as spatial positioning of objects, active versus passive words, remains for future work. Yeah, this is interesting to me as kind of a future work direction. So we saw that Right. Fine-tuning for this counting specific task ended up producing just a little bit of a loss of performance on these other ones. But I'm curious, like, if you did this for 100 different tasks, like, how much would that impact it? Right? Could it be a method of improving these foundation models is basically going one by one through all of their weaknesses and improving the performance on each of those things? Something to think about. All right, Food Station, you sent me a huge text here. What are you saying? You are a new entrant. Yes. Uh, is it possible to write something like software as a service that can generate income on its own? So, I mean, passive income is possible, but it's very difficult and rare. The best example I have seen of that is people who succeed in making a viral phone game. ML software is much more hands-on and requires lots of tuning and improvement over time. So it's hard to think of an application where you could just write some code and then profit. Maybe for a limited window of time. Hard to say. Yeah, Food Station, it's going to be difficult just because there's so many, especially in ML, you're competing against a lot of these big companies. So it's very difficult to compete against Google and OpenAI and Microsoft, right? They just have so much more money to spend on training. They have proprietary data sets. I think, yeah, maybe like assistant, maybe some kind of specialized assistant as a service or something in generative art. There is money to be made, but there are lots of people asking that same question right now. Food Station, another thing you can do is make yourself another YouTube channel and not make any money, which is what I do. Do it for the love of the game. Okay, well, actually, there was one more thing I wanted. I wanted to know what the object detection model that they use here. I want to know what this one is. Object detector. Let's search object detect. Come on. Come on. They have to tell us what it is. 500K steps on 64 TPU v4 chips. Atom optimizer. Damn, they really don't tell you. That is insane. Count bench, clip, text, 12. CFAR. Yeah, they straight up just don't tell you what the object detector they used is. It's probably some kind of internal TensorFlow one or internal Google one, and that's why they're not telling you. But hey, what are you gonna do about it, you know? Cool, so that was teaching clip to count to 10. This is work by Google Research, Tel Aviv, and Weizmann Institute of Science, came out just recently. Again, this was recommended by someone in our Discord channel. You should go ahead and join that Discord channel. There's links on my YouTube and then links on my GitHub as well if you want to figure out where that is. But feel free to join and you can continue to ask questions there if you want. But yeah, cool little paper. They went above and beyond. I like that they trained a generative model. I like that they released a benchmark. I like that they did this part here. The zero-shot accuracy on common benchmarks. Very nice, very clean, very well implemented paper, and this is good research. I love to see it. Thanks for listening. Hope you guys have a great week, and like and subscribe as always.